Ladies and gentlemen, welcome to the second IMO showcase session. Again, we'll have two speakers, and it is my pleasure to introduce the first speaker of the second session. We have Dušan Djukić from Serbia. Probably many of you have heard of him, from the IMO Compendium. So if you have read the book, he's the one in charge. And he has been involved in the IMO for many years at this point. He was an IMO contestant like 20 years ago with 2 or 3 gold medals. And today he will be our speaker, so let's welcome him.
Thank you, Cesar. Well, so today I wanted to talk, I was thinking about which problem I would talk, and I thought I could talk about one of my problems I created for the IMO. Although it is mine, I still think this is not such a bad problem. It was the number 6 from 2006, almost 20 years ago now. Okay, so this is what the problem was like. Suppose you have, okay, here I'll try to draw a big picture. You have a convex polygon. To every side of this polygon, you assign the triangle with the largest area that is inside the polygon. So, for example, to this side here, we would assign the vertex that is most distant from it. That would be this vertex here, right? In this way, to this side, we have assigned a triangle inside the polygon. Okay, we make such a triangle for every side of the polygon. The question was, prove that the sum of areas of all these triangles over all sides is at least twice the area of the entire polygon. So if this is, let's say, the side AI, and this area is PI, then the question is, prove that the sum of all these PIs is at least twice the area of the polygon. Okay, so this is the statement of the problem. Okay, this was not an easy question, probably needless to say. And I don't know if we will have time to show all solutions to this question. But how are we going to estimate the sum of all these areas of these triangles? They don't get along very well. So you don't expect you can, if you assign to this side some other triangle, you don't expect there will be a really nice way to add this and that. As I said, they don't get along well. So what are we going to do here? One of the ideas here is, okay, once we have drawn these two triangles, maybe it would be easier to, instead of considering the areas of the big triangles themselves, to try to consider, to try to replace them by this region between the diagonals. So there will be two of them here. Okay, so here, just for simplicity, the picture looks like this. So for now, we behave as if there are no vertices of polygons somewhere here. Let's not complicate the picture. So all we see is this. Okay, so let's take a look at the shaded area here. What did we say? Pi is this. Wouldn't we like to prove that the area Pi is greater than the shaded area? That would be wonderful if we could, because that would probably imply the solution. Because the sum of shaded areas over all sides would probably exceed twice the area. Why is that? Now we wonder, wait, maybe these shaded areas are easier to add up than the triangles that were given in the problem. But how are we going to put these shaded areas together? First of all, if we want to do that, we will probably need to assume there is an equal number of vertices on either side of the big diagonal. But we can always assume that, because we can always draw some phantom vertices on the sides to divide the sides. And one more thing that will turn out that we need is that we would like these two shaded triangles to have the same area. We'll see very soon why this is needed. Okay, so our picture now looks like this. Once we have settled to check these shaded triangles here, we would like to show, first of all, that the sum of the shaded areas is at least twice the area of the big polygon. So let's have a look what we have. I'm going to draw another big picture, this time with an even number of vertices, like A1, A2, up to AN. And here it's going to be AN plus 1, AN plus 2, and up to 2N. I can do this, okay, we agree. Because even if my polygon was not like that, what will I do? I'll just add a couple of vertices here. These will be the new vertices of the polygon, and the internal angles at these vertices are 180 degrees. Why not? Are we doing any harm with that? No. So we are at this. And let us draw the big diagonals. The big diagonals, I mean the diagonals AI, AN plus I. Okay, sometimes I have a habit of writing very small letters, which become smaller and smaller. So if this is not readable, I hope someone will tell me, especially for someone who is sitting on the back rows. So we are drawing these big diagonals. Where is our shaded area? Here it is. So for every two diametrically opposite sides in the polygon, we have one such shaded area. So how many shaded areas do we have? Exactly n, right? N for a polygon of 2n vertices. Okay, so this one is going to be S1 if it corresponds to the side A1, A2. So there will be S1, S2, S3 up to Sn. So let me first show that S1 plus S2 plus up to Sn is going to be at least the area of the polygon. I promised this will hold, and I also claimed that this will somehow help me to solve the problem. Okay, so I said that these shaded areas get along better than the triangles do. How are we going to prove this? Okay, let's draw a couple of other big diagonals. Of course, the picture is not very good, so it may look like these three diagonals meet at a point. No, of course not. I'm not claiming that. All we have is a number of diagonals and many areas between two consecutive diagonals. So how are these regions between these diagonals cover all of the polygon? Okay, let's see. Let's think about it this way. When we take the union of all these shaded areas, does this union cover the whole polygon? If it does, we are done. So does it? Let's see. Does it cover this point here? Let's see again. We have a diagonal and a point which is not on the diagonal. As this diagonal moves over other diagonals, at some moment, this point is on the other side of the diagonal, right? You see what happens? Now it's to the left of my hand, but when I rotate, it suddenly comes at some point to the right of my hand. So does it cover every point? Yes. And this automatically means that all these shaded areas together cover the entire polygon. So the sum of the shaded areas is at least P. P is the area of the big polygon. Okay, so how is this going to help us for the problem? As I said, we are going to need something else. We are going to make an extra assumption about these diagonals. This is strange, but we will soon realize why we actually need that. Because here, if I want to claim that Pi is greater than the shaded areas, what will be the condition that will guarantee this to us? Well, what I know is that the product of these two unshaded areas is equal to the product of these two shaded areas, and blah, blah. But if I want to be sure that Pi has a greater area than the shaded area, I need what? I need these two triangles to have equal area. In other words, I need this polygon to be a trapezoid. Because if it is, we know for sure that Pi will be greater. Why? Because if we assume that this side is larger than this side, then automatically this triangle, this white triangle, will be bigger than the area above it, because this is greater than that. So if you add the small shaded triangle below, it means that the area of the whole triangle PI is greater than the sum of these two areas. Okay, so I would like these two shaded triangles to be of the same area. How do I get that? In this big polygon, that would probably mean that I would insist that always the same area remains on the left side of the diagonal as I rotate it, which will automatically lead to the new assumption. Let's assume that every diagonal of all of these diagonals, that each diagonal divides the polygon into two halves, two parts of equal area. So we add this strange condition because we have just realized it would be very nice to have it. So assume that each diagonal bisects the area of the polygon. Nobody can read this, but you've heard me, so you know what I mean. Okay, so can I assume this? Am I not losing too much generality here? No, not at all. Not at all, because given any polygon, okay, I'll mess up every single board here. We have 4 boards, I will probably mess them up all. But for now, okay, given any vertex, can I always draw a diagonal that divides the polygon into 2 halves? Well, no, but if I add a couple of phantom vertices, of course, yes. So for any vertex, cannot I find a unique point on the boundary of the polygon so that the line through these 2 points bisects the area? Yes, of course. For every vertex, I can find a unique other point, which I will also call a vertex. So I add these new vertices whenever I need them. Okay, so what I'm assuming? I'm assuming that the big diagonals A1, AN plus 1, A2, AN plus 2, and so on, all bisect the area of the polygon. That's okay? So what happens now? The sum of the shaded areas is P, at least P. The sum of the big triangles I assigned is greater than the sum of the shaded areas. Well, wait a second. We have this shaded area, but we count it twice, for this side and for this side. So the sum of the assigned big triangles is actually greater than or equal to twice the sum of the shaded areas. And the sum of the shaded areas is at least P, which means that the sum of the assigned triangles is at least 2P, and the proof is complete. So that would be one way to solve this question. I don't know, how much time do we have, boss? Okay, good. So maybe I have time to mess some more boards here and try to show you the other solution. So again, let's have let's consider a big polygon, P. What we are going to do in this solution, so this is your second solution, what we are going to do is we are going to simplify this polygon by a sequence of steps. one step at a time, and after every step of ours, the area and the assigned triangles will change predictably, which is very important, and the polygon will become simpler. What do I mean by a simpler polygon? Well, for example, isn't a polygon with lots of parallel sides simpler than a polygon without parallel sides? Isn't a polygon with fewer vertices simpler than a polygon with many vertices? Such things. So, okay, to every side, there is a vertex on the other side of the polygon assigned. Let's take an instance of them. Okay, so this is one triangle, and here is another one on the neighboring side. Okay, we can assume without loss of generality, because we will for sure find such two sides that the assigned vertices are not the same. Not all sides are assigned the same vertex. So we can assume that in front of us we have a picture like this. So what am I going to do? So, of course, if I draw a parallel to the side at the top vertex, it won't meet the polygon again. It won't hit the interior, definitely. Also, if I draw a line parallel to this other side, through the opposite vertex, it also won't hit the interior. So, wouldn't you agree that the red triangle on this side remains the same if I move this point here? If this vertex here moves here. Of course, the area remains the same, but I'm not going actually to replace this point. I will still need it. I'll keep this vertex, but I'll add a new one. Well, wait, why am I adding vertices if I said I want a simpler polygon? Because if I add this beautiful vertex here, then I get many parallel sides. So if I add this vertex as a new vertex of the polygon, so now my polygon will look like this. We have added this piece here to the polygon. We have just got two pairs of parallel sides. What will happen to the big triangles when I did this? When I do this, what happens? By how much does the area of the polygon change? The area, okay, we may have several vertices here. To all these sides, we have assigned this vertex, because the farthest vertex from all these sides will obviously going to be this vertex here. Also, neither of these vertices here inside will be assigned to any side of the big polygon. So we don't need these vertices inside too much. We can simply replace all of them by this top point. What did I say? What happens with the area of the polygon? The area of the polygon has increased by this much. So if I call this area S, then P has increased by S. What will happen to the sum of the big triangles? The sum of the PI? By how much will that change? Well, the areas on these sides and on most other sides remain unchanged. But the areas on these sides inside will increase a little bit. So, for example, instead of these three triangles, now I have these two triangles that include this vertex. So the sum of the PI's has increased by how much? By exactly the same. The sum of the shaded of the big triangles has increased by exactly S. So if I want to show that the sum of PI's is at least twice the polygon P, obviously the statement is getting stronger if we move to this polygon with parallel sides. So it's enough to prove for the new polygon. Okay, when we apply this small operation a couple of times, we'll get lots of parallel sides. Okay, what do we do with these parallel sides? What can we do with them? Why is this polygon actually simpler? Well, can we remove it somehow? Let's have a look what happens. Okay, let's suppose that I have a polygon with two parallel sides. I can always, even adding some new vertices if I need them, I can always assume that these two sides that are parallel also have equal length, right? If they don't, I'll just cut off a small part of one of them and add it as a new vertex. So, okay, on this picture we assume these two sides are equal and parallel, and in other words, this thing here is a parallelogram. What do I want to do? Guess what? I want to remove the parallelogram and glue the polygon back. So my new polygon will now, when I move this part here and glue it on this diagonal, what will I get? I get something like this, right? Where these pieces will be parallelograms. Okay, so in this way, when I do this, I will definitely decrease the number of sides. And definitely I will get a simpler polygon. Okay, so what happens when I remove this big red parallelogram? Okay, it's still not red, but let's make it red. Okay, so if I change from the big polygon to this smaller polygon upon removing these small parallelograms here, what will happen to the area? what happens to the area of the polygon? It decreases by how much? By the area of the red parallelogram, right? So P will decrease by P minus, okay, how do I call the area of the parallelogram? Let's say T. So P will decrease by T. Now what happens with the sum of the big triangles? When I do this, which of these triangles are actually going to change? Well, all of them are going to change. For example, by how much will the area assigned to this side here change if I shrink the polygon like this? Okay, previously the area was this. And when I do this, when I move this vertex to here, the assigned area will now be this. By how much did this change the area? Well, it will be exactly the difference of heights from these two vertices onto this side. Actually, maybe it's better to see if I look on the other side. What will happen to the area assigned to, let's say, this side here? This side will now move. Now it has become that side. This one. What happens to the assigned area? Initially it was this. But when I do the change, what happens? Now I'll have the same triangle over this side. So this black area has become this red triangle here. What is the difference between the black triangle and the red triangle? It is precisely half the area of this parallelogram here. So the sum of assigned areas over all these sides changes by exactly the number, the area of this belt here, which is itself equal to the area of the parallelogram, right? And the same will happen to the other, on the other side. The same happens to the triangles on these sides here, analogously, right? So what happens? The sum of PI's decreases by exactly 2 times the area T. And the area, the difference of the areas, the sum minus twice the polygon P remains the same. So when I do this small change, the difference that I want to show is positive, does not change. So I remove these parallelograms one by one, and what will be left at the end? Probably nothing when the difference is 0, right? So if I do this change, the difference does not, the difference the sum minus twice the area of the polygon does not change, but when I do that by adding a new vertex, this difference actually becomes smaller, makes the statement stronger. So in this way, it will be enough to show the statement for the simplest polygon, and the simplest polygon is when you remove all these parallelograms. The simplest polygon is the empty polygon. The best polygon is the empty one. And for that one, the difference is what? 0. So again, we are done in this way. So that would be another possible solution to this question. Where you are actually trying to simplify your polygon because your initial polygon is not easy to control. Okay, so that would be it for now. Now tell me, do you have any questions?
All right, let's thank Dusan. Great talk.
Thank you, people.
If there are questions from the audience, please go ahead. Any questions? This was actually a very beautiful problem. Okay.
I just want to ask for the first solution, how did you finish the problem after you got that each diagonal bisects the, like after you can assume each diagonal bisects the polygon?
Sorry, can you repeat?
Yeah. So in the first solution, we proved that we can assume that each diagonal bisects the polygon.
Yep.
So can you repeat how you finished the solution afterwards?
After that, when I assume that each diagonal divides the polygon into half.
Yeah.
Because if I do this, I know that these two triangles will have the same area. And when I do this, okay, why did I forget my markers? What did I say? So, if I have this, here, of course, I don't claim these two sides are parallel, right? But what I know is that the sum of assigned triangles on these two opposite sides will be at least twice the shaded area, because each assigned triangle will be itself larger than the shaded area. How do I know this? Well, can I assume without loss of generality that if I call this point O, can I assume without loss of generality that A1O is greater than OAN plus 1? So this segment is larger than this segment, right? If I can, then does this also mean that this side is larger than this? So also AN plus 2, O will be larger than OA2. All right. So this means automatically that this triangle here is larger than this triangle. So the area of this triangle here is larger than the area of the lower shaded triangle and the upper shaded triangle, because this part is greater than that part. So that's what I have. That's why I have the sum of assigned areas here greater than the shaded twice the shaded area.
Okay.
And when I sum up over all pairs of opposite sides, I get the result.
Okay. And one more question. Do you remember how you came up with this problem?
What?
Do you remember how you came up with this problem?
Sort of, I don't know. My first idea for the problem was prove that at least one of the assigned triangles is at least 2 over n times the area of the big polygon. So this is the first statement I came up with. But when I found this solution, I realized that the statement becomes stronger if I divide the sides into equal pieces. So then I moved a little bit and improved the statement to obtain this statement, which is actually stronger than my original statement.
Thank you.
Any other questions?
Okay, so in the second solution, to construct a parallelogram, you add 1 point to basically the longer side.
Yeah.
When you remove the parallelogram,
You mean when I do this?
no, on the fourth board.
Or when I am about to remove the big parallelogram?
When you're about to,
Yeah.
okay, so first you construct the parallelogram, right?
Yeah.
You add 1 point to the longer side.
Yes.
Then you remove the parallelogram,
Yeah.
but you are still left with a small segment from the longer side. And if the remaining polygon doesn't have the property that any two sides are parallel anymore, because you just removed.
Oh, you mean when I glue it back? Well, this means I have just translated this part of the polygon by this vector here. So it must fit correctly. You see these two vectors, they are the same. That's what I assumed. Because what I'm removing is not a trapezoid, it's a parallelogram. So I'm just going to translate this part here by the vector I have drawn. So yes, it fits properly.
Yeah, I know it fits. It's just that, can you get to the empty polygon? Because may I come to the board to give you an example? Because it's a bit hard to.
Sorry, can you ask?
Go to the board to draw exactly what I mean?
You mean to draw why
Yeah,
it
I want
fits
to-
properly?
It's easier if I draw.
Yeah.
Okay, let me.
If you want, but wait, for that we'll definitely need this.
Yes.
Yeah.
Okay, so just give me a marker. I could have drawn it here. Okay.
Here.
Okay, so basically you say that you have a polygon which has all parallel sides, right?
Yeah.
And let's say this is the one. What you're saying is that, okay, so let's just complete it. You are saying that we pick this point,
Yep.
we draw this parallelogram,
Yeah.
we remove it,
Yeah.
and we are left with like this thing. Tuk, tuk, tuk,
Yes.
and tuk, tuk, tuk.
Yes.
My concern.
So we are getting this, right?
Yes, exactly. My concern is what do we do with this side? This has no corresponding pair.
Let's see. Well, we still have this part, right? So
Did you remove this?
Yeah. So we still have this part. It's here.
Yeah, you have it, but you have no corresponding side on the other end. And if you repeat this process, you are not guaranteed to end up with the empty polygon.
Yes, of course. But we don't care too much about that because we also have the first type of operation.
Yes, but
So now we'll have two sides at which
But in that
We
operation,
assign-
you are adding vertices, and here you are removing vertices. Do you have a guarantee that you will?
Oh, what you are getting actually, you are decreasing the number of non-parallel sides. You are decreasing the number of directions in which the sides go.
Oh, that.
You see, I never add a new direction.
Oh, I think I get it.
So that's the important point here. That's a good question, yes, but we don't worry about that. That's not going to happen.
Oh, okay. I understand. Thank you.
Thank you for the question.
Any other questions, please? One more question from the audience. Okay, if there are no other questions, let's take